Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, today we will discuss, about the question paper based on the chapter number 1, 2, and 3. So the question that I have give you last week is actually based on the properties of pure substances and also the first law of thermodynamics, but concentrating on the closed system, okay, not open system. Okay, so chapter 1 just for the introduction. So the introductions is quite easy. You just understand the definitions, and then from there you can deliver your definitions in the question and answer. Okay, I will share the question. Okay, so far the question we want to discuss is based on the final exam question MEC 451 thermodynamics, June 2018. Okay, so how you can get this question? Now we want students to assess all the questions, all the final exam questions based on the online. So one method that you can access is through the library. Okay, PTAP. So let me show how can you get this question. Okay. Uh, I share entire screen first. All right. Okay. You can type EQPS, Electronic Question Paper System. Okay. So this is the website Tersawang koleksi UiTM. So get in the website. Okay, when you are in the website, so you must sign in with the Google. Okay, that means you have your students' emails. Okay, sign in. Okay, yang ni saya masuk melalui saya punya account Kamu masuk kamu punya account, you will have your own account channel. Okay, in the exam paper. So from here, you click on the exam question paper system. Okay, click there. So from here you have a lot of separate contents and either example exam paper, OPEX, e-books, online databases, and etc. So from here, I want to find the final exam that we will be discussed. So whether you want to type here or whether you want to search here, okay? So we search MEM 462. That is your course. Okay, kita try cari MEM. So what happened now? MEM 462 is not available because this is the first. Okay, this is the first course that the student attend. So tak ada lagi tidak ada lagi final exam. Okay, recorded. So I will click on MEC 451. So there it will come up all exam papers that have recorded from year maybe year 2010 or 2011, okay, or 2005, okay. So from here I want to choose we will discuss on September on 2018 section 2, okay, section 2. So go there. Okay, this is the exam paper. So you can download straightly from here to your PC or just view from here. So I just want to view from here because this question I can access anytime I want. So we go to question number 1. Okay, question number 1. Actually, question number 1 and question number 2 is based or will be covered on chapter number 1, 2, and 3. Okay, so this number 1. Question number 1A. Okay. Provide the definition of system, surrounding, and boundary layer. Okay, this is the example of how the question, the cases or question that will be asked to you in the test, exam paper, or exam. Okay, so for A, you have to provide the definition of system, surrounding, and boundary. And then it's also, I also want you to construct a schematic diagram of the typical diffuser, label the thermodynamic system, boundary, and surrounding on the schematic diagram. Okay, two things. Okay, ada dua perkara here kat sini. Two things that have in here. That's mean number 1, just provide the definitions, and number 2, draw the schematic diagram. Okay, okay. So so this is the answers for the system. So you just put down or you just give the definitions of the system, surrounding, and boundary layer, boundary. So this can be you have learned in chapter number 1. So actually the system is a quantity of the matter or a region in the space chosen for study. That is system. Okay, and then the surrounding is the mass or the region outside of the system. Okay, so that is definition for the surrounding. Definition for the boundary. It is the real or imaginary surface that separated the system from its surrounding. So this is 3 definitions that you have to provide in the answer scheme, in the answer. So number 2, based on the diffuser. Okay, diffuser iaitu diffuser in Malay is called pencapah. Okay, real boundary layer is around real boundary layer that's cover all the system. So the system of the analysis is diffuser. So this shape of diffuser as a system, and then it been labeled by the boundary, real boundary. Real boundary, that means the wall of the diffusers. Imaginary boundary is the expectation or imaginations of the boundary. Okay, of the boundary. So the questions ask about the label the thermodynamic system, boundary, and surrounding on the schematic diagram. Okay, so this is how you label the the question 1. Okay, so system, boundary, and surrounding. Surrounding actually the mass or region outside of the system. Okay, complete question number 1A. Any questions you want to ask regarding this example? Ada tak?
No, sir. Yes,
Okay,
sir.
faham Alright. Okay, alhamdulillah. We go to the B. 1B. Okay, 1B, it asks, okay, it asks about provide, okay, provide the definitions of greenhouse effect. Okay, one, and then briefly discuss the potentials, long-term consequences, and possible solutions to these problems. Okay, this is about chapter number one. Okay, about the renewable energy or energy at the end of chapter number one. Okay, provide the definition of greenhouse effect. Okay, let's look what what let's discuss and analyze what these answers of this question number 1B. So definitions of the greenhouse effect. So you can put it like these definitions. This is on your pemahaman sendiri ya, on your based on your understanding and put it together in the words. Okay. Trace amount of gases in the atmosphere such as CO2, water vapor, methane, and nitrogen oxides cut like blanket and keep the earth warm by blocking the heat radiation from the earth. Okay, that is a greenhouse effect definition. So from there, you will get 2 marks. Okay, the total mark is 5. And then potential long-term consequences. It means excessive amount of these gases disturb the delicate balance by trapping too much energy. So which will cause the average temperature of the earth to rise and the climate at some localities to change, and this is referenced as global warming or global climate change. Okay, that is the potential long-term consequences. So possible solutions, how we can give the solution for this case or this phenomena by reducing the net potentials of CO2 by consuming less energy. For example, we can use energy efficiency cars or uh, planting trees or and etc. That's me a lot of examples can you put here. Okay, so the marks here when you answers like this, you will get 2 for the potential long terms and 1 for the solutions. Okay, the total mark is 5. Okay, that is for 1B. Okay, number 1 A and B. Question number 1 A and B normally is is on the definition. Okay, selalunya this is the starting question. So selalunya akan tanya tentang definisi and then also tanya benda-benda yang agak for starting, okay, untuk pergerakan mulaan. Okay, bukan terus jump to the calculations. Okay, not straightforward to ask about the calculation. Okay, selalunya macam itulah soalannya. Okay, okay, C. Okay, C based on the calculations. Okay, firstly, when you get the questions of thermodynamics, firstly, this is my experience. Okay, I want to share with you, and also how do you can tackle the question. Firstly, you have to understand the question. understand the words that used in the question. That's why you have to read chapter number 1 and understand it, because chapter number 1 is based on the definition and also the definition of every words term that used in thermodynamics. Okay, so we go to the question C. A 1.25 meter cube, okay, rigid container. Okay, rigid container, that is something regarding of thermodynamics you have to know. Rigid container is filled with 6.5 kilogram of R134a, okay, refrigerant 134a, and an initial temperature of negative 30 Celsius. Okay, sentence number 1, you have to understand, okay, and get the idea and try to imagine how this view of the rigid container filled with the liquid. So also in this question you also have to know the working fluid. Okay, saya selalu tanya working fluid at that situation. So when you know the working fluid, so you know how to solve the question. Okay, next sentence, it said the container is then heated until the pressure reach 140 kilopascal. Okay, sketch any phase change diagram to show this process and determine number 1, 2, and 3. Okay, that is the sub question. So firstly, you have to understand the question. Okay, as I mentioned berkali-kali, okay, every time I mention when we do the discussions based on the example, I always mention that please list down, okay, please list down what has been given in the questions. Okay, so in this type of question, we list down what has been given. Okay, number 1, substance that has been used in this analysis, that is refrigerant 134a, the substance. This substance, actually you have to find whether the R134a is in a liquid phase or in a gas phase, because this substance can be changed phases when it's goes to the different properties. Okay, properties, what I mean properties in here is temperature, pressure, volume, anything. Okay, because this substance can change its phase to liquid or gas to liquid. Number 2, this is a closed system. Why? Because it is a rigid container. So the rigid container is a box. Okay, a box rigid. Rigid that means tegar, kuat. Container kebuk yang kuat, tegar. So that is a rigid container. So it's a closed system, tertutup, okay, fully closed. So this is a closed system. So you have to apply the equations or the analysis based on the closed system. Okay, closed system. Okay, then the process. The process that have in this question is constant volume process. Okay, constant volume process. Why? Okay, based on the second sentences, the container is then heated until the pressure reaches 140 kilopascal. Heated. Okay, heated. The container is a rigid container, so the rigid container is constant volume. because that container will be not increased. The volume of that container, rigid container, will be not increased whatever it is heated. Okay, heated dia tak akan increase. So that's why we know that this is a process in the closed volume process. So the mass that been given is 6.5 kilogram, and the volume is 1.25 meter cube. Okay. So before we go to step number one, or before we go to the analysis in detail, you have to think, use your akal, think. This is the working fluid here is refrigerants. So when it use refrigerants, working fluid, so the applications to solve this problem is easily based if you go or if you use the properties table. Okay, use properties table to solve this question. So when we want to deal with properties tables, step number one, that means at step number one, you have to find a specific volume. Okay, specific volume V1. Why? Because specific volume have in the properties table. Okay, let's open the properties table. Okay, okay. I will open properties table. So, okay, these are properties table functional. So we go to the try to find the tables of refrigerant. Okay, 134. TS, table refrigerant, saturated water, water, all water, table A11, saturated refrigerant 134. Okay, this one, saturated refrigerant, table A12, table A13. So basically, we will find the A11 first. Okay, A11 for saturated, because we don't know whether this refrigerants is in the phase of mixture or superheated. Okay, go to A11. A11 6. Okay, A11. This is A11. Okay, that's why in step number one, first what you have to find, as I show in the examples, V. Okay, specific volume. Why we find specific volume? Because in this question only volume has been given. Okay, even 1.25 meter cube. So we use these properties to find specific volume, and with specific volume disebabkan uh, it have in properties table. Okay, specific volume ada. So from there, when you find specific volume, V1 is equals to 1923 meter cube per kg. Okay, by dividing 1.25 to 6.5, you get the specific volume. Okay, it also shows heated the initial. Okay, it also shown it also give the initial temperature of negative 30 Celsius. Okay, so the first T1 is negative 30 Celsius. So based on the properties tables, you go to negative 30. Okay, this one, when you look here, temperature side, okay, saturated refrigerant temperature tables, you can find negative 30 is in between. No, you have negative 30. Negative 30, the specific uh, for saturated liquid line is 0.0007. The specific volume at saturated vapor is 0.25. Okay, but your calculations is 0.19. So from the tables, T negative 30 Celsius, what it can be conclude that the calculations is bigger than VF but smaller than 0.2 Vg. So what happened? We know that when these situations appear, we know that the state one is in the in the mixture region. Okay, because it is under the hill. That means kalau saya lakarkan bukit tu, so the right the right side is a saturated vapor, left side is saturated liquid. So now the point is in between left and right. So that's why it is in this phase one, state number one is in the mixture region. Okay. So number one, it's want you to find the initial pressure of this working fluid. Okay, initial pressure. So P1. So you have know the you have defined, you have determined the phase one region. It is a mixture. So since state one is a mixture region, then the initial pressure is blah blah blah. That's mean 84.43. How you determine this number figure? Okay, look back on your properties tables. 30 Celsius. So the pressure now P1 is 84.43 because V, that means specific volume that you have determined, is in between this VF and VG. So it at this state one is in the saturated line. Okay, saturated line. Okay. Then number two, the final temperature of the R refrigerant 134, the final temperature. So the final temperature, how you want to find the final temperature? That means the container is then heated under the pressure reached 140. Okay, 140 is the P2. Okay, 140. So 140. Okay, we're starting from the quality. Okay, because okay, I will continue the analysis of these answers. That means P1 we have known it is as a P saturated 84.43 kilopascal. So when you know phase number one is a mixture, so what happens? You have to find the quality of that working fluid at state one. So the quality is based on the equations. You can find in the chapter number 2. So V1 is equals to VF uh, V V1 is equals to X VFG minus VFG. Sorry. How it up? Okay, V1 is equals to X VFG plus VF. Okay, that is the quality. So the value as X1, rearrange the equations. So you know the V1, VF also at 30 negative 30 Celsius. VG, VF, you can get the from the properties table, put in the equations, then you get the V1, sorry, X1 is 0.8. That is the quality. So to find, and then we find the enthalpy at step number 1. Enthalpy is HF plus at is FG. So put the numbers, figures based on the properties table at negative 30 Celsius. Okay, so you look at negative 30 Celsius. So find enthalpy HF. This is the value. HFG, this is value, and HFG, this is value. Okay, the nilai X, the X value has been determined by calculation. So put all together the values, and then you will get H1 is 199.51 kilojoule per kg. Okay, so we go for state number 2 because the refrigerant has been heated, okay, to pressure 140. So now at this situation 140, firstly you have to find whether state number 2 is in which region. What I mean, whether is it in the mixture region or is it in the superheated region. So to do that, okay, you know that this is a constant volume process. In other words, in thermodynamics words, isochloric, okay, constant volume process. Constant volume process, also known as a isochloric. Okay, this is an isochloric process. So V2 is equal to V1. So you have the numbers here because it is a closed rigid container. So based on the tables, P140 kilopascal. Okay, we try to find P1. This is temperature table. Okay, go forward. Look on the pressure table. Is it a pressure table? Yes, pressure table. Look on pressure table, kilopascal, 140. Okay, at this 140 kilopascal, what happened? You look at Hg. Okay, Hg is 239.16. That is Hg. What is Hg? Hg is the enthalpy point or the state point that have in the saturated vapor line. That is Hg, enthalpy at uh, uh, a vaporization line. So compare with the calculation H1 that have been calculated previously. So that is H1. Okay, we also can compare with the volume. Okay, volume. If we want to compare to H, but we count 199.1, 199.51. Okay, this one 100 29. Oh, sorry. Okay. Okay, from table A12, that is for pressure 140 kilopascal. Okay, make the comparison. Okay, for the volume, uh, specific volume. So you have calculate the first specific volume. Okay. Uh, so V2 also equal to V1. So now look on the 140 Vg. Vg is 0.14 compared to V2. V2 is 0.192. And what happened between these numbers, it it will give the conclusions that the specific volume at state number 2 is bigger, greater than specific volume at G. So we can conclude that the state number 2 is in the superheated region. So when it is in the superheated region, straightforward use superheated region table. Okay, you go forward for superheated refrigerant tables. Find the final temperature. Use these tables. You know the pressure. You know also the volume. So to use these properties, to use these tables, I have mentioned previously. You must know at least two properties. So in this case, you know the specific volume and also pressure. Pressure 140. That means P is equals to 0.14 megapascals. And then the volume. Volume is sorry, not volume. Specific volume is 0.19. So try to find specific volume 0.19, 0.19, okay, 0.19, 23, 0.1923. So it is in between, okay, in between uh, 60 to 70 temperature. So do the interpolations. So calculate it based using the interpolations, and then from there you will get T2 63.36 Celsius. That is answered for number 2. Okay, number 3, the amount of heat, the amount of latent heat to perform this process. So you want to know the latent heat. So the amount of latent heat, so using this formula, okay, the amount of latent heat, the formula is delta small h times by m, okay, this amount of latent heat. So you have to find H2. Okay, H2 can be found using the same methods when you want to find the temperature. Okay, so based on these properties, you have V 0.192 something, and then now not based on the temperature but the enthalpy. Okay, enthalpy. See, here is the enthalpy H. So it is between 306 315. So 306 315. Do the calculation. You will get H2 is 309.67. So put the H2 in the equations, then get the answers of the latent heat, 716.07 kilojoule. Okay, then sketch any phase change to show the process end. Okay, sketch. So at the end, sketch the PV diagram. So this is the process of uh, isochloric. That's mean constant pressure at PV diagram. So at state number 1, it is a mixture region. At state number 2, you have defined that it changed to the gas phases, gas phase. That means superheated region. Okay, this is the answers of this question. Okay, itu dah soalan mukadimah. Okay, actually this is the starting point of the thermodynamics. Sebelum kita pergi ke nombor 3, 4, 5. So this is the concept and the theoretical how you can calculate for the thermodynamics based on chapter number 1. Okay, chapter number 2, that's mean pure properties of pure substances. Okay, any question?
Yes, sir.
Okay, tidak ada Alright. Can I continue? Boleh
Yes, sir.
Alright. Okay, now we look on the other questions. Question number 2. Question number 2 is about number A is definition. B is calculations. Okay. So look at the marks here. For of course for definitions, knowledge, connective level 2, 5 marks. And if you look on connective level 3, different cost outcome, it gives 15 marks. So this is calculation based, quite critical, okay, difficult, but you can do it from this example. Okay, we go for the question 2A first. Briefly explain 5 types of moving boundary works and sketch the respected PV diagram to illustrate their process. Okay. Okay. So 5 moving boundary works. That means 5 moving boundary work and also sketch this process. Okay. So 5 moving that as you read in chapter number 3, in thermodynamics, for boundary works processes, it have for the boundary work process, it have 5 processes. Okay, the simple words that I want you to give you that in thermodynamic course here, we only focus on these 5 processes of boundary works. Okay, so number 1 is isochlorics, that means constant volume. So you just define what is mean by constant pressure. The process where the volume is remain unchanged throughout the entire process, also known as the isochloric process. Okay, also known of the isochloric process. So the PV diagram is like as shown macam ni lah. Okay, so you have to show the vertical straight line of that process, and the line must be straight. Okay, and it have step 1, step 2, and also please remember to put the arrow here, show that where the process, show that the directions of the process. Okay. Okay. Number 2 is constant pressure process. Constant pressure process. Constant pressure process. Oops. Sorry. Known as isobaric. Okay, isobaric. Isobaric, that means the process where the process is remain unchanged. The pressure is remain unchanged. So to show the graph, you have to put the straight line. Okay, straight line, but the line must be horizontal because it's constant pressure. Number three, constant temperature process, named as isothermal process. So what is definition of isothermal process? Please give the definitions. It is the temperature that remain unchanged. That is constant pressure. So the graph must be curved. Okay, the graph must be curved because it have follow the equations PV equals to C. Okay, this is a law of isothermal process. So that's why it gives the curved line of the graph. Number four is adiabatic process. It also a curved line because it follow the law, the equations of PV power by K equal to C. That is a law of adiabatic process. And the definition of this adiabatic process is the process that occurs without transfer the heat or mass between the thermodynamic system and its surrounding. That means at that situation, uh, heat and mass do not move, okay, do not transfer, okay, at that situation. That is the assumptions or the imaginations that we have to imagine. We have to we have to imagine of adiabatic process. Okay, and this adiabatic process also known as the isentropic process, where the value n is equals to k, or sometimes it's equal to lambda. And the number five process is polytropic process. This process obey the relationship of PV power by n equal to C when n is a polytropic index, any real number except k. Okay, so that is the relationship. That is the definition of polytropic process. The graph PV diagram also it show curved line. Regarding with the equations or law of polytropics. Okay, PV power n equal to C. Okay, that's his answer for A, 2A. 2B. Okay, 2B. Okay, this is quite this because this is for the calculations. It give, okay, the question mentions that an argon gas is filled in 0.025 meter cube piston cylinder device with electrical heater inside it at 120 Celsius and 125 kilopascal. That is the first sentence. Normally, the first sentence it will give you the tips. What is about the case about? Okay, in this case, it gives that the argon gas. So this is the working. This is the working fluid that used in this question is gas. So gas. So when you know it a gas, the solutions that you have to do the solution is based on the calculations using first law, using ideal gas law. Okay, in subchapter of ideal gas law or equations of state. Okay, that is the solutions. That is the approach that you can use in this question to answer. Okay, and then it also show in first sentences piston cylinder device. piston cylinder device is also the device that have cylinder and piston inside it. So we imagine or we consider these devices, two items put together. This is closed system. Okay, this is closed system because at that situation, no either hole that or any hole that have in that device. So we call that is a closed system. And also in that device, it put the electrical heater inside it. Okay. So sentence number 2, it said the argon gas is then expanded polytropicals to 75 Celsius and 66 kilopascal when the 120 volt and 5 ampere electrical heater is turned on. Okay, when we switch on the electrical to give voltage and ampere to the heater, then the gas inside the electrical heater expand because it has been heated by the heater. Okay, okay, that is the maksud ah, that is the of the sentences. Okay, and then it also said that if the heat loss, okay, if the heat loss through piston cylinder device to the surrounding during this heating process is estimated as 2.5 kilojoule. Okay, it got the heat loss go outside of this device, and by taking specific heat at room temperature, so you want to consider this is only the situation at room temperature. Determine the time taken to complete this process. Okay, how long? Okay, the time taken to complete this process. Sketch the schematic diagram of the system and PV diagrams to illustrate this process. Okay, the answer must be in sketching. Okay, sketch schematic diagram. The diagram that involved is PV diagram. Okay, let's go for the analysis. As usually, list down what has been given, because what when you list down what the data that have been given, it will make you to focus more on the question. Okay, that's why the tip is list down. Try to understand the question first. If you don't understand the question, how do you want to answer the question? Okay, so given is argon gas because the working fluid used here is gas. That is why it highlight argon gas. So argon gas, so you find R because when argon gas, you will think about perfect gas, ideal gas, equation of state. In that equation, it have gas constant value. It also have uh, specific heat at constant volume, CV, and so on. So that's why argon gas, you find R argon 0.2. Where to find R argon? Okay, go to properties table. Find tables that show all the gases that have in the world. So this is the properties, molar mass, gas constant, critical point properties. So from here you can see, you can find argons, AR, molar mass of argon, and gas constant. Okay, this is gas constant, R for argon, 0.2. Okay, so that's why 0.20 list down. CV also from these properties, you can get CV, argon, volume. Okay, we try to find CV, argon. Okay, this CV, argon, gas constant, and CP. This is value for CP. This is value for argon. Okay, this is value for K. That means K is Cp over Cv. Cv, okay, and then V1 0.025 meter cube, T1, P1, T2, P2, voltage 120 ampere, and Q out 2.5. Okay, Q out. That means if the heat loss through the piston during the heat loss is 2.5. Okay, heat loss. Heat loss. That means uh, heat is out from the system to outside. That is heat loss. So when it happen, when you use approach Chengal approach, heat loss to the surrounding, we put it as positive 2.5 kilojoule. 2.5 positive, not negative. Okay, heat loss. When heat gains to the system, heat, we put it negative. Okay, in this case, heat loss to the system. Go outside to the system, that is 2.5, positive 2.5. Okay, this is a schematic diagram that show state number 1, piston 1 to piston number 2. Sorry, this is the same piston, but the locations is different. State number 1 is first locations, and then expand of this gas will move the piston to state number 2. Okay, so heater, and then plug into the voltage source and electricity. Okay, so this is a schematic diagram. Okay, to start these calculations, as I mentioned, this is a gas. Working fluid deals with this equation is a gas. So the approach of the calculation, the solutions is based on the equation of state or ideal gas. But you also know this apparatus device is also a closed system. So it's a closed system. So you know to apply the first formula for the closed system of for the analysis of energy. We use energy balance for the closed system. That's mean energy balance for the closed system. Lastly, will have defined it from chapter 3. That's mean first law of thermodynamics. We have defined it first law of thermodynamics for the closed system. And the equations for first law of thermodynamics for closed system, also known as NEFS, non-flow energy equation. Okay, NEFF. So, okay, back to the energy balance of the closed system. So, energy balance, we know the energy in minus energy out is equals to differences of energy in that system. So, we find energy in and energy out. Energy in terms of energy and works. Okay, energy and works. And energy that move the molecule. So Q in plus W in is equals to MQ in. So is equals to the delta U. Energy out, energy system is delta U plus delta KE or delta PE. So to make it more easily, this is a first law of thermodynamics first system. Okay, so you know that the last equations that you want to use in the first law of closed system, non-flow energy equation, is Q minus W is equals to delta E. That is a NF. That is a general equation for first law of thermodynamics. Okay, so in this system, for a closed system, energy, total energy, it has a internal energy, kinetic energy, potential energy. So when we deal with a closed system, we ignore kinetic and potential energy, because in the closed system there was no moving. There is no moving happen in this. We assume the moving is very small, and we can neglect this kinetic energy and potential energy. It only have internal energy. Okay, internal energy in the rigid or in the closed system. So we will get lastly delta U is equals to work energy in. Okay, it's from it comes from W in minus Q out minus Q out work play out from energy that's come from the process, not play, polytropic. Okay, energy in, work in is come from electricity. This energy from electricity. Q out is it is because it has the question has mentioned that have heat loss. Work polytropic, it because work out because of the movement piston. So it transfer the energy heat into boundary work. Okay, that mean in here is polytropic work is equals to internal energy in this all system. Okay, so we have to find the polytropic boundary work output based on the formula. W polytropic out is blah 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 P2 P2 V2 minus P1 V1 over 1 minus N. So and then you have to find the value of each pressure if it not given in the question. So for this working fluid is using a gas. So the ideal gas equation state that PV is equals to MRT. So from here, M you can determine using all the given data. Okay, so you got M is equal to 0.0382 kg. So why you want to find M? Because M it will be used to find volume 2. Okay, but at the state number 2, volume 2, this is based on the ideal gas equations, energy at state, PV equals to MRT. So for state number 2, you have M, you also have R argon, you also know the temperature at state number 2, pressure at state number 2, so you can get the answer of volume at state number 2. So using the polytropic index, this is a law of polytropics. Okay, the law of polytropics. Why it said polytropic? Okay, why it said polytropic? Because in these questions, it say it expanded polytropically. So the question has mentioned that the process involved in this case is polytropics only. That's why we calculate, we want to find the answer based on the process of polytropic. If the process is mixture, polytropics, and other on so on, so you have to find this based on the processes that have been given in the question. Okay. Okay. Oh, sorry. So now based on the polytropic index or equations law, polytropic law, you know that law of polytropic is P1 V1 N, or as example as simplest way, PV power by N is equal to C. So elaborate using this, and then from here you want to know the value of N. So from this all the rearrange the equations based on mathematical, then the N value you will get the answer of N. Okay, and from the N you put again the value of N into the equations of work polytropic out, so you get the answers. Okay, that is for uh, part 1 to define P or work polytropic. You also have to define work electricity. Q out have been given. So now electricity and the delta U. Okay, for 2 we and then we find delta U first. Okay, the delta U from ideal gas, you know that the delta U is mCV delta T, or we take the formula of CV. Okay, CV is equals to delta U over delta T. That is formula of CV. So rearrange this formula, and then you get delta U. M, because we want to convert the joule per kilogram to the unit of joule, kilojoule. So that's why we times mass in these equations. Okay, delta U is negative 0.5367 kilojoule. So for electrical works, it based on the formula that I show you just now. So work in, you have got all the values for these equations, for this unknown uh, term. So just put it the answers or the value into these equations. Lastly, you will get the work in of that work electrical, that into the device is around 2.6876 kilojoule. Okay, so that is a work in. Okay, but you do not answer the question yet, because the answer wants to know how long it will take to make these situations become like that. So knowing that the electrical work is also calculated as these equations, okay, work in is equals to V I delta T over 1000 kilojoule. This is in unit of kilojoule. So we want to know the time that take to do that situations. So rearrange these equations. Lastly, it will give the answer of time 4.479 Celsius. Sorry, 4.479 second. Okay, that is the time taken to give the heat or the phenomenon of energy balance of the um, devices. Okay, in the devices. So it also want you to sketch or give the answer in the sketching PV diagram. So you know this is a polytropic process. So of course you just draw the line, the curved line, because it is a polytropic process. So the curved line have a law. That's mean PV power by N have been defined, have been determined. So just put 1.55 that you have determined N equal to C. So this is a diagram that give the answer of schematic diagram. Okay, that's it to cover to answers the question of 2. Okay, any question for now at the moment?
Tak ada, sir.
Tak ada. Okay, alhamdulillah. Okay, That is question for June 2018. Okay. Actually, this final question is as same same as what you will see in this final exam, also the test exam. Okay.